In this video on light, we're going to get into two different things. We're going to talk about the cost of lighting, and we're also going to talk about our first model of light, which we call the Rey Model of Light. So far, we've looked at how various light sources produce light, but now let's consider the cost of using different sources of light. And primarily, we're going to start by talking about electrical energy. And here in Ontario, electrical energy costs about 13 cents per kilowatt hour, which might not mean a lot right now, but we're going to get into exactly what that means. Here we see kind of a whole little fan chart. If you were curious about how much electrical energy costs in different provinces, and I believe this is from just last year, so it's very recent data, you'd be able to kind of see what the average price is. So here in Ontario, we're a bit more expensive than places like Manitoba or Quebec, even. But thankfully, we're not paying the prices of Northwest Territories or Nunavut, which is paying about 38 cents per kilowatt hour as opposed to our 13 cents, almost 3 times as much as what we have to pay for the exact same amount of things. Let's go over a couple of definitions here, though, before we get into understanding how to solve a question about how much something might cost to run. A watt, for example, is a unit of electrical power, whereas a kilowatt is 1,000 watts. And so a kilowatt hour is 1,000 watts of electrical power operating for a time period of 1 hour. I know we've talked a lot about rates and ratios in grade 7 and grade 8, and so this kind of gives you an example of one of those interesting rates and ratios that compares kilowatts, a unit of energy, with hours, a unit of time. The symbol for watts is a W. The symbol for kilowatts is a lowercase k and an uppercase W, and the symbol for kilowatt hours is a kW dot H, or kW per H. To understand how to calculate the cost of lighting, let's go through an example together. Let's see how much it would cost to leave a 60-watt light bulb on for 10 hours if the electrical energy costs 13 cents per kilowatt hour. So if we were taking a look at the rate from Ontario, and we were taking a look at just one 60-watt light bulb on for, let's say, an average 1 day, an average 10-hour day. Think about if you were scaling this up in terms of a house, you'd have a ton of these light bulbs. And if you were scaling this up in terms of other different devices, this is a 60-watt light bulb. Your computer could very easily be running 300 watts to 600 watts, so 5 to 6 times as much. And so you can see how different devices around your house could start to add up when it comes to electrical costs. So first of all, in order to solve this, let's begin by converting 60 watts to kilowatts by dividing by 1,000. So 60 watts is the exact same if we divide that by 1,000 as 0.06 kilowatts. Right? I'm just kind of converting. It would be the same thing if we were converting meters to kilometers, that kind of thing. Second, we want to calculate the number of kilowatt hours by multiplying the power in kilowatts that we just figured out by the number of hours that we're running it for. So if we are running this 0.06 kilowatt light bulb for 10 hours straight, we multiply 0.06 times 10 and we get 0.6, move the decimal one spot over, kilowatt hours. Finally, we want to calculate the cost of leaving the light on for 10 hours by multiplying the number of kilowatt hours by the cost per kilowatt hour. So just take that 0.6, times it by our 13 cents here in Ontario, and we would see that on average, to have one 60-watt light bulb on for 10 hours of the day would cost about 7.8 cents per day for that light bulb. Which again doesn't sound like a lot, but when you scale that up to the many light bulbs in your house and the many other devices in your house that produce electricity, you can see how this can start to add up over the course of a week, over the course of the month, or even over the course of a year. Therefore, the cost of leaving the light on for 10 hours is 7.8 cents here in Ontario. Again, if you were in Northwest Territories or Nunavut, you'd have to almost triple that in order to get their rate. But you see how different things can kind of add up as we take a look at the cost of electricity compared to how much watts or how much energy it would use to be able to produce that same light. So the less amount of wattage something is going to be or use, the less energy cost it's going to have, and therefore the more energy efficient it's probably going to be as well. The second thing that we're going to be getting into and talking about today is going to be the Rey model of light. This is one of the very first models of light that we're going to be taking a look at as we understand how this model works. Well, the idea that light is a form of energy can't explain certain properties of light. For example, how can this energy make shadows? When someone passes the screen during a movie, a shadow is cast over the screen, as we see in that picture. Light from the projector can't bend around the person to reach the screen. And so observations such as this tell us that light has to travel in straight lines. And so the Rey model of light is based on that observation. A ray is a straight line that represents the path of a beam of light, and it's one way that we can try to understand how light works. We can use the Rey model to predict where shadows will form and how large they will be. And we do that using Rey diagrams. So here we see two different Rey diagrams that have a light source, and you'll see we have straight lines coming out of that light source. We also have different solid objects that are in the way, and we see that behind the solid objects, we end up having this shadow spot where the light rays can't pass through. And we see that the further back, or the closer we have those objects to the light source, the bigger the shadow is going to be, that kind of thing. Because light radiates out, something that we also talked about previously as well. You can use the Rey model to predict where shadows will form, how large they'll be, and the Rey diagram shows us how to use that Rey model. We just draw straight lines coming off or radiating off of that light source. And if it hits an object that it can't go through, well, you're going to end up with a shadow behind that source. Light beams travel out in all directions from a source, but you need to draw only a few rays to be able to predict the size and location of a shadow. You need one that kind of hits the very top of the object and one that hits the very bottom of the object, and then kind of scale it out to be able to see how large that shadow should appear. Notice in our diagram that we always draw the ray that travels closest to the object that is blocking the light. The Rey model can also help us understand what happens when light energy reaches different types of materials. So here, for example, we have another Rey diagram, but now we have three different types of materials. And we're going to get into this a lot more as we go a little bit further on, but as light travels through different types of materials, it reacts differently. So for example, when light passes through clear substances, like a window, the ray continues along the straight path. We say that these clear substances are transparent. Transparent means that it can go kind of straight through. No obstruction, no issue with that. And some examples of that we have are air, water, window glass, the lenses of our eyes. We're going to talk about eyes a lot more later on. These are all transparent that allow light to kind of pass through normally without any obstruction. When you hold a piece of paper in front of a light source, you can still see light coming from the other side. However, you can't usually see images, or at least not clearly, because the paper ends up scattering the light a little bit. The paper bends the light rays, and some get through, some get bounced off in different directions, some actually get reflected back as well. Some of the rays bounce off the back of the paper. Substances such as paper are therefore said to be translucent. Translucent means it can let some things through, some light through, but not all. And so therefore you end up having kind of this, this effect where you're not really able to see what's on the other side. We might have this, for example, in our house when we see different things like frosted glass. Some types of glass and other plastics are said to be translucent. Many materials also completely block the light and prevent any of it from passing through. We call these materials opaque. We see that example in the very middle. No light's getting through. It's just all getting reflected back or all getting absorbed, but none is going through that object to the other side. Some examples of this would be a desk, a wall, a house, a lot of different things that just completely stop it, that don't let any light through. And so if you had a light source on one side, you would not have any of that light coming through on the opposite side. And it's opaque materials that cast the majority of the shadows that we have as well. This is the end of what we're going to be getting into today. In our next section of videos, we're going to be beginning to take a look at reflection and what happens when some of these light rays hit an object and bounce off that object.